Hi guys, this is Charles 2, and this is my Physics 2212 Lab 2 on magnetic field. The purpose of today's lab is to observe a small bar's magnet interactions with its surroundings and measure distance dependence due to the bar magnet. Some things to know about barhand is Biot-Savart's law and the distance dependence formula for a bar magnet. Our assumption is that we're going to act as if the bar magnet is acting as a magnetic dipole. So our procedures is we're first going to align the magnetometer with the Earth's magnetic north. Then we'll use a magnetometer to find the magnetic on and off axis field. Then we'll get the constants to use for the magnetic field produced by bar magnet. So the system is a magnetic bar. Surrounding should be everything else around it. So here's my data. As you can see, we measured the distance and try to get the resulting magnetic field from those distances. So we had 3 trials to make sure we got the most accurate data we could find. And then here's the magnetic field resulting from those distances. And then we got the averages and plotted these points on this graph. As you can see, the resulting line would have been y equals negative 2.998x minus 14.686. We'll then use that equation we found right there on the next page to find the magnetic dipole moment mu. So from our distance dependence formula, Ln k is equal to negative 14.86, and then n is equivalent to just a slope. And then basically you'll solve for k, and you get 3.5187 times 10 to the negative 7. And then you make the Biot-Savart's law equal to magnitude of the bar equals to the k times r to the n. And then you get that magnetic dipole moment is equal to k times r to the n plus 3 power times 10 to the 7th over 2. And then because n is negative 2.998, r, you basically get like this thing right here is equal to 1 because it's close enough to 0th power. You get the magnetic dipole moment at 7.555 area meters squared. Then we plug that value of the magnetic dipole moment to right here 1.755 to create, and then we create the magnetic origin. Here's a constant of u over 4 pi. And then we create a function to create the magnetic field. Over here, we're creating the visualizations for the on-axis and off-axis moments at different distances. Here, we get the d-perp from our experiment, and we're finding the 45, like the visualization in 45 degrees from the axis, and our result, something like that. Purple arrow here, oh small, but yeah. And then our result is here. As you can see, the magnetic field perpendicular compared to on-axis is larger, and it goes in the opposite direction. The resulting distance we get is 0.238578. And then we get the magnetic field at 45 degrees at that distance is right here. And then we also get that magnitude. So some errors is obviously like errors in measuring distance, stuff like that, small stuff. And then in this experiment, what if we orientated the setup to compensate for magnetic north? What if we hadn't done that and instead laid out our meter stick at some intermediate angle with respect to Earth's magnetic field? How the results change? Well, then the Earth's magnetic north field would interfere with the results that we got, which would change all the data that we marked down. And if we had two identical magnets and did the same experiment, but we stuck the two magnets together at end to end, what would I expect? Well, my expectation would be that the magnitude would double, but it would maintain the same direction as from before.